Alrighty, let's see. Are we live? We are live. Perfect. All right. Welcome to another stream on my Robomagellan robot Kybernetes 2. And thank you for coming back after a month of me being offline. I was out backpacking in Yosemite the last couple of weeks, which was a really, really nice breakaway from the work cycle, right? All right. So where did we leave off? We have been in the last stream we were porting the Arduino sketch that controls the motion the Arduino sketch of the motion controller in my Robomagellan robot. We were converting that from just a simple Arduino sketch into a project based on an RTOS called ChibiOS. And ChibiOS is more commonly seen in the STM32 space, although it has maintained an AVR port over the years, although the AVR port is not nearly as fully featured as the STM32 port. As we ran into, we did have a couple of warts from the last from last time, where we essentially the external interrupts, the GPIO interrupts on the Arduino, or on the Atmel AVR that's inside the Arduino. There is ChibiOS doesn't have support for what they call pad events, which are per GPIO interrupts. It doesn't have that implemented. It doesn't have that implemented for the AVR. So we essentially went through and manually added support for these for the external interrupts. That's what this the register setting down here. Oh, right, I have to zoom in so everyone can see. Right. So that's what the register setting here was with the EICRA EIMS external interrupt mask register. That's what all these were. Was setting up the external interrupts such that setting up the external interrupts such that we could use them, because again, support's not built in. And the other thing we bumped into that took a bit of time to solve was that the encoders, not the encoders, the servos in the chassis, the one is the speed controller, one is for steering, one is the steering servos. Those are attached to the timer 1 outputs on the AVR. And by default, ChibiOS on the AVR uses timer 1. Well, actually, I don't know if saying by default is correct, but at least in the configuration that we had pulled out of the sample, it was configured to use timer 1 as the clock source for switching tasks, whereas I needed to use timer 1 for controlling the servos. So what we did was we enabled something. I won't get into it too much, but I reverted from using something called tickless mode back to the standard tick mode, and the major difference between the two is the standard tick mode. There's basically a timer that fires on a fixed interval, and let's just say that's 1 millisecond. I can't remember if it's 1 or 10 milliseconds in ChibiOS. But by default, it'll have this timer that fires on a specific interval to run, to do any of the RTOS kernel functions, switching tasks, running timers, etc. Tickless mode, what it does by default is it uses a higher precision timer on the AT-Mega 328P, which is what's in the Arduino. There's only one 16-bit timer, and that's timer 1. Timer 0 and timer 2 are only 8-bit timers. So they can only count to 255 before they reset. So what tickless mode does is it gets rid of that periodic that fixed interval tick function, or tick interrupt, and rather it figures that any time the kernel's going to sleep or doesn't have anything to do, or knows that there's an event that needs to happen in the future, rather than just waiting for the next tick, what it'll do is set the timer 1. Essentially, it'll set a higher accuracy timer to essentially throw an interrupt specifically at the time that the next event occurs, rather than waking up and being like, oh, there's nothing to do yet, and going back to sleep, waking up and then finding out there's nothing to do. So either way, it's the reason that that's beneficial is that it uses less power because it means that the CPU can sleep longer when there's nothing to do. But again, we only have one high accuracy timer on the 328P that's in the Arduino, that's on the Arduino Uno that I'm using. Whereas something like STM32, which is what ChibiOS mainly would work with, all ARM CPUs have, okay, I really don't want to make that claim, but I'm fairly certain that all ARM cores, especially in the microcontroller space, have a unit called the SysTick unit, system tick unit, which is a timer specifically for essentially doing timing tasks in your logic, so that all of the more advanced timers are free for doing hardware. But either way, so with that out of the way, what we had to change this, I think it is in the ch config, yes, CS time delta. If this value is 0, that uses the classic periodic tick. So yeah, we had to change this in order to get the to free up timer 1 so that I could use it for servos. But that's there. Let's see, were there any other warts of note? Right, we also had, because of the whole interrupt situation, we ended up building the encoder logic just into this main function here, with this main class, which is getting very long and I need to clean up at some point. But today, what we're going to be doing is adding support for the current sensor that is in my logic power supply on the robot. And just if you're joining us for the first time, let me just flip over to my my cell phone camera here and show you what the robot looks like. We'll switch to the phone camera, and so this is what the robot looks like. It's an RC truck that's been modified into a robot. One of the boards in here is what I call the logic power distribution unit, which connects to connects to a 3-cell LiPo battery that's mounted under the robot. There are 2 batteries, one that runs the motors, one that runs the logic. On the logic power supply side, that's then stepped down to 5 volts to provide a couple of USB ports that power everything from the Raspberry Pi to the camera to the GPS and the onboard Wi-Fi router. But one of the pieces of hardware that I put in that logic power distribution unit was a current, more specifically, it is a voltage and current sensor so that you can measure actual power usage by something, both immediate and continuous power usage, or because the sensor has what's called an integrating analog digital converter in it, such that it can measure power usage over time, otherwise known as what's called a Coulomb counter. So today the goal is we're going to be adding support for this sensor, because I haven't had support for this sensor before, even in the existing codes. This will be new functionality, and now that we're using ChibiOS to make to give us better control, mainly we're using it for better control over the I2C hardware in the Arduino. So we're going to be adding support for some of the other I2C sensors, because that was the whole point of this migration in the first place. So without further ado, we're going to jump into the schematic for the robot, or not for the whole robot, but for the logic board, just so you can see where this is. This is the KiCad schematic for the logic power distribution unit. It has, it's fairly straightforward. Basically, there is a couple of voltage dividers that provide various reference voltages in the system. Basically, there's a low power, low battery sense input. There's a battery critical input. Basically, one trips at I think 3.5 volts per 3.5 volts per cell, which means the batteries, I believe 3.3 volts per cell of the LiPo, which I believe represents about 90% of the battery is used. So that triggers a low power battery logic power low sense signal. There's a logic battery critical signal, which I believe I have set at 3 volts per cell, which makes sense because it's a divide by 3 and it's a 3-cell battery. So yeah, the reference voltage in this system is this provided by this 3-volt Zener diode reference supply. So if either of these drop below 3 volts output, then the signal throws. But this low sense triggers when the battery's at like 90% used, and then critical triggers at 0, or at least basically the minimum safe voltage on the cells. So the low sense triggers a GPIO pin on has a GPIO output that can be read, and then the critical sense will shut down all the voltage regulators. It's a hardware protect feature. If you go below 3 volts a cell, the whole thing just turns off the regulators and stops all the power draw off the battery, or at least almost all of it. Just a couple of microamps aren't handled, just because there is some, you need to supply power to generate the reference voltages. And then that 12 volts thereabouts coming in from the battery is then sent through this current sense resistor here on the regulator in. This is an INA219B current power voltage sensor. It's connected over I2C to the chassis microcontroller. And then that 12 volts is then run through. This doesn't really show the regulator because the regulator is an external voltage regulator board I bought from Pololu, I think, years ago, that I integrated. But Pololu, either way, it goes through a 5-volt regulator, and then that's just broken out to a bunch of USB-C connectors to supply power. Either way, so the robot has a I2C connection to this board, and also that I2C bus in there, it connects to this current sensor. It connects to an IMU, which we may get to do today, but we'll probably do in a future video. It also connects to the onboard, though, what I call the kill controller, which it basically, unless the trigger's being pulled on the radio, it turns off power to the motor control. It turns off power to the motor controller, so that there's a out of loop dead man switch, because I crashed this thing into a river once because I had the kill switch was just a soft kill switch, and the batteries got low, and it caused the microcontroller to just keep resetting. And unfortunately for me, I was using the Parallax HB25 servo something, what I don't remember what they call HB25 motor controllers, which my Arduino was resetting. Those weren't. And if those lose their input signal, they don't shut down. They just keep running the motors at whatever it was. So I completely lost the ability to shut the robot off. And it just ran away and ended up driving into a river. So I'm still scarred from that. Just scarred. So I very much tend to try to build out-of-band kill switch systems. So on my robot, on any robot that can outrun me, the remote kill switch, everything can, I designed them such that everything else on the robot could have failed, and I can still turn it off. Just from a protect your investment perspective. But either way, so all of the schematic really just, I wanted to show that there's this INA219B current sensor just in the hot path from literally directly battery current sensor, then that supplies the rest of the board. So this current sensor is literally before everything in the robot, on the logic power supply side. So I believe I set the A1, A0 to ground, so it's going to use whatever the default address of the sensor is. So we will just minimize that, and I already pulled the GitHub link to all of this code is github.com/technoman117/Kybernetes motion controller. So all the code's here. I already pulled up, this is the data sheet for the INA219 and 219B sensors. Let me just zoom in on that there for you. Fit page width. I think I can just... What about editing red and blue LEDs for evil versus good mode? I could steal some of my NeoPixels out of another system. So oh yeah, Rafael and Santos. Yeah, this is gonna be my first time using it. I mean, ironically, I put this sensor into this robot years ago, and I was just like, oh, the battery runs for, because all this whole thing's like Raspberry Pi. I think the logic side of this only draws like, at worst case scenario, only draws like 20 watts. So one of these big lipo packs that I've got, like this thing can be running at full power for like 5 hours before the batteries drain, and it's just rarely ever running at full power. So you can plug it in the morning and it'll last all day. So I never really bothered looking at the current. I never really bothered actually getting around to using the current sensor because the battery lasts all day. So this will be the first time. So we're going to be writing some ChibiOS support for this sensor. And somebody has probably already done this for ChibiOS because this is a very popular sensor. But just because I hate myself, I'm going to do this from scratch, maybe. Or we're going to try anyway. And so let's figure out where we want to start. So let's go to, well, let's just scroll back up to the beginning of the datasheet. So since it's 219, I connects over I2C, available in 2 grades A and B. I've got the B grade in here because I wanted the higher accuracy, and the whole higher accuracy, higher precision. So it is higher accuracy, but specifically it can sense smaller. It's got a better current sense amplifier in it. So what that means is that the way you measure current draw in one of these systems is you use what's called a shunt resistor, and typically these are extremely low resistance. They're very precise, but they're very low resistance. So in the case of this one, I'm using an 8 milliohm resistor, and so I mean, if you divide the Ohm's law here, V equals IR. If we were to say have a full 12 volt drop across the resistor, divide that by 0.008, it's huge. You measure large amount of current can pass through without blowing too much power, or I squared R, I think is the power loss. So either way. So the higher precision INA219, the B variant, you can use a smaller shunt, or a smaller value shunt, so you waste less power. Let's see. So we're going to come in here and then... All right. So we have this whole robot stack. Okay. So let's... Because I've powered up the robot already, let's open another VS Code window here. And we're going to connect to the just so we can have it. We're going to connect to the robot. I believe I've got this. No. Okay. So connect current window to host. We're going to connect to the robot, which is connected to my home network, and we're going to type in the. What I get for using 20-character passwords. Okay. All right, yes, and of course there's always a VS Code server update, so that's coming down. I'll download VS Code server onto the robot. Okay. Specifically, I'm just opening this up so I can get the Python environment that I've written most of the robot's control code in. And before somebody freaks out and worries that I'm doing heavy lifting in Python, I'm not. The Python's pretty much just a bunch of glue logic on top of a bunch of C++ libraries. So don't worry about it. All of the heavy algorithmic compute work is done in C++ and other languages that are compiled and fast. And really, it's just the high-level management logic of things is written in Python. It's just none of the performance-intensive parts. Okay, so now that we've opened the robot, we will not open file. We're gonna open a folder, come in here, we're gonna projects and Kybernetes Python, open that, bring up the robot, and if it's smart, it might figure out my Python virtual environment. That would be nice if it did, but it's never guaranteed. All right, so let's... Python extension is still loading. Python, activating extensions. Code is only valid if suffering was involved. Okay, so what do we got? Python. Oh yeah, depth AI virtual environment. Perfect. It actually loaded up. I have to open a new little terminal window down here in order to get the virtual environment. Yes, depth AI. Perfect. We have a virtual environment for the robot, which contains all of the depth AI logic that runs the camera. But other than that, what am I doing here? All right. I don't plan these streams ahead of time, really, except for the topics. So I don't actually know how to solve. I don't have a pre-existing idea of how I'm going to solve this. So I think what we'll do, where we'll start at least, is I have a status message that is sent 50 times a second from I believe it's 50 times a second. Yeah, every 20 milliseconds, 50 times a second. From the motion controller, I have it send a status packet to the Raspberry Pi. And that is done through this controller update task. It goes through here, it reads the encoder, does some stuff, updates PID controllers, and eventually comes down here and sends a status packet to the robot. Realistically, I think just to start with, whether this is a good idea or not, or whether this stays, because we're going to be refactoring a lot of this. Eventually, I'm trying to get this video out on doing. Trying to finish writing it, really. Recording it won't take long. I'm just trying to finish writing it on doing reliable, how to reliably send data over unreliable transports is, I think, the working title. Reliable connections over unreliable transports. But so I'm gonna do a video hopefully the next week or so that we're gonna cover those concepts, and then on one side we're going to use that to implement a better serial interface protocol to the robot's controller here. And then the other side of it is going to be using that same serial protocol to do the firmware update on that bare metal project that I haven't put out a video on in months. But either way, it keeps bouncing on my head and I can't focus on one thing. But either way, so we're going to start by attaching essentially whatever data coming in from this current sensor to the status messages. I think where we'll begin. So, and I believe in here I do sample the get struct, check if any transitions need to happen, kill switch status packet. Okay, right. So inside this controller update task, which runs 50 times per second. It does do an I2C operation to reach out to the. This is that kill controller thing that I was. Basically, it handles the remote kill radio. It handles the remote kill switch. It also tells you what the status of the remote radio is, but or the remote, or the trigger, the steering wheel, whatever. All of the inputs on the controller. So we'll essentially do our so somewhere in here we're gonna need to do. Sample the current sensor. So let's go look at this overview here. So the INA219 is a digital current sense amplifier with I2C and SM bus compatible interfaces. Provides digital current voltage and power readings necessary for accurate decision making and precisely controlled systems. Programmable registers allow flexible configuration for measurement resolution as well as continuous versus triggered operation. Detailed register appears at the end of the datasheet starting with table 2. All right, so let's start with, there's a lot of math in here that we'll have to get through, but let's start by, INA219 address and slave address pins. So if A0, all right, you can do some wacky configurations here. I connected both of these to ground, so we're gonna have this base hex 80 address up here. So, INA supports the fast or high-speed modes. Oh, so it supports really high-speed I2C, but the Arduino doesn't. So we're going to be using the 400 kilohertz I2C on this whole thing. So let's start with figuring out, I2C is I2C, but, it uses... Oh, so it uses, okay, so I2C, sometimes you can do 8-bit frames, and sometimes you can do 16-bit frames, ACK by INA, yeah. So it uses the word format, timing diagram for SMBus alert. That's one thing that SMBus has that I2C doesn't. It's not particularly well defined how I2C devices generate interrupts. Theoretically, you can do something based on pulling the line low to send events, but SMBus actually, I believe SMBus actually has a mechanism for sending interrupts over the I2C lines, but we won't be worried about that. We won't be touching that. Register maps. All right, there are, thankfully, really not that many of them. As it seems, there are 6 of them. So there's a configuration register that we can write to 00 configuration. We can write, I'm assuming we write all the configurations there. And then we've got, that's a read and write register. And then we've got shunt voltage measurement data, which is a read-only register, bus voltage, read-only register, power measurement data, read-only register, and current read-only register. And then there's calibration out. So we have to write the configuration, and then we write the calibration, and then everything else is read-only. Perfect. That sounds really nice. Okay. So, register contents are updated 4 microseconds after completion of the write command. Therefore, a 4 microsecond delay is required between completion of a write to a given register and a subsequent read of that register without changing the pointer when using SCL frequencies in excess of 1 megahertz, but we're at 400 kilohertz. That's fine. Okay. Power register and current register default to 0 because the calibration register defaults to 0, yielding a 0 current value till the calibration register is programmed. Okay, so we can just 16 volt FSR. Okay, we'll have to do some math. Okay, so first of all, let's make this long file even longer. Okay, so we're going to, let's see, so I say const expression int current sensor address. We already mentioned that it's going to be hex 80. I can't type. Wow. All right. Because if we looked at that section of the data sheet, device address, if we connect both A1 and A0 to ground, it is 1 followed by a bunch of zeros, so that's hex 80, highest bit set. If we just remember that, we have A1 and A0 both tied to ground, and so A1 and A0 tied to ground, we have this hex 80. So, const expression int, current sensor address, hex 80. The INA, okay, so, writing and reading serial interface, I2C SMBus, reading and writing to the INA219. Accessing a particular register is accomplished by writing the appropriate value to the register pointer. So this might not be using that, well, actually, the question is whether it uses the old, very, very old yet very, very common method of basically I2C EPROMs. If you want to set the register pointer, you go to write mode, you write the register value, and then you do a repeat start, and then do whatever other access you want. So I don't know if it does it. So okay, so writing a register begins with the access a particular register is accomplished by writing the appropriate register for table 2 for complete list of registers and corresponding addresses. The value for the register pointer is shown in figure 18 is the first byte transferred after the slave address byte with the RW bit low. Every write operation requires a value for the register pointer. Okay, that's real normal for I2C. Okay. Writing to a register begins with the first byte transmitted by the master. This byte is the device address with the read-write bit low. INA acknowledges the receipt of a valid address, the normal I2C stuff. The next byte transmitted by the master is the address of the register to which data will be written. Okay, so that's the standard I2C EPROM register protocol thing that every device under the sun uses, usually. The register address value updates the register pointer to the desired register. Okay, the next 2 bytes written to the register address by the register. The next 2 bytes are written to the register accessed by the register pointer. So it's 16-bit frame. The INA219 acknowledges receipt of each data byte. The master may terminate data transfer by generating a start or a stop condition. Okay. Every write begins with Okay, so it might not support remembering. No, it has to. Never mind. Sorry. It's just works like an I2C problem. When reading from the INA219, the last value stored in the register pointer by a write operation determines which register will be read during a read operation, right? So if we want to select a register, we then do a write with the register we want to select, and then we do a repeat start, and then ask it for a read. We'll read that register. Pretty standard I2C protocol. Very standard pattern with I2C. It's not part of I2C, but it is how a lot of people use it. It's how pretty much all these devices use it. Okay, so to change the register pointer for read operation, a new value must be written with the register pointer. The write is accomplished by issuing a slave address byte with the read-write bit low. Again, write is active low, followed by the register pointer byte. No additional data is required. The master generates a start condition or repeated start condition and sends the device address byte with the read-write bit high to indicate initiate a read command. Next byte is transmitted by the slave and is the most significant byte of the register indicated by the pointer. Okay, so it's most significant byte first. Good old big endian. The byte is followed by an acknowledgement from the master. The device transmits the least significant byte. Master acknowledges read to the data byte. The master may terminate data transfer by repeating a not acknowledge after receiving any data byte, generating a start or stop condition. If repeated reads from the same register are desired, it is not necessary to continuously send the next register pointer bytes. It retains the register pointer value until it is changed by the next write operation. Okay, so the question is, if I want to sample all three registers and just cycle through them, do I have to keep changing the address, or will it do what I2C EPROMs typically do in auto increment? This makes it seem like it probably doesn't. So, we'll just I will try both. Nothing will hurt it. Okay. So read that. It's just standard I2C stuff. Registers. So we've got, we'll just do some definitions here. We will say define INA219 configuration register as 0. We will say define INA219 shunt voltage as 1. Define INA219 bus voltage as 2. And I believe, the measurement here is shunt voltage is the voltage across the shunt resistor. So you're part of your measuring power draw computation. Shunt voltage that will directly correlate to the current flowing through the system. The higher the shunt voltage, the lower, the overall system resistance will be lower the more current it is drawing. So that would mean, so more shunt voltage means you're losing more power across the resistor because the system is drawing more current. I think higher shunt voltage means higher current draw, if I remember my Ohm's law stuff correctly. Either way, so shunt voltage is the voltage drop across that shunt resistor. Bus voltage is essentially just measuring the battery voltage. And then power is the chip computing overall power draw. And then you can also measure the current, the computed current flowing through the system. Let's finish our little defines for our registers here. And it's always kind of good to wrap these in parentheses because remember that in C and C++, a define is just a straight up substitution. So that's always kind of a good form to put constant numbers and defines inside of some kind of parentheses if it's just a constant number. Oh, bus voltage, power. Oh, wow, I didn't even write register after it. Okay. Register. Bus voltage. Register. Also, if anybody has any questions for me, please don't hesitate to ask. I do try to keep my eye on the chat. Calibration register. Perfect. Okay. So, looking at the configuration register, all INA219 16-bit registers are actually two 8-bit bytes through an I2C interface. Perfect. By default, it resets to 399F. So that would be 0011. Because that's 3. So 0. Oh, it even writes it down on the bottom. Nice, thank you. Yeah, 0011, 1001, 1001, 1111. Yeah, that makes sense. Okay, so bit 15. Setting this bit to 1 generates a system reset that is the same as a power on reset. Resets all registers to default values. This bit self-clears. Perfect. We probably want to do that at the very beginning of our program. So we'll calculate CRC. What have I done here? Acquire bus, release bus. All right. All right. So we'll probably want to issue a reset here. Resets all registers default values if it self clears. Bus voltage range. 0 is a 16 volt range. 1 is a 32 volt range of the default value. We're gonna have to look up what that means. Bus voltage range. PG, PGA at the shut voltage only. Sets the PGA. It's probably programmable gain amplifier. So sets the PGA gain and range. Note that the PGA defaults to a division by 8, which is a 320 millivolt range. Table 4 shows the gain and range for the various product gain settings. There's probably going to be a little... So, I mean, we scrolled past all the math, and I'm pretty sure that all tells us how to compute from our desired system parameters what we should be using here. So, we'll scroll back up here in a bit. Let's just finish reading through this. All right, so all of this controls, so both zeros, it's a gain of 1, so plus minus 40 millivolt range. The reason it's plus minus millivolts is that this is a bidirectional current sensor. So if you were to, say, integrate a battery charger, like the typical system architecture for this current sensor is that you'd basically put the battery, you'd put the current sensor, and then you could have, in parallel, your device and then the battery charger. And if the current is negative, you're charging the battery. If the current is positive, you're draining the battery. Well, it really depends on which way you hook up that shunt resistor. I'm pretty sure that a positive... yeah, I think it's right. I think positive is going to be draining the battery, negative is going to be charging the battery. But either way. And then we've got the BADC, bus ADC resolution and averaging. These bits adjust the bus ADC resolution, 9, 10, 11, or 12 bits, or set the number of samples used when averaging results for the bus voltage register. I believe that... no, it says right here, and I'm wrong. Okay, so... then we got SADC, which is the shunt ADC resolution and averaging. These bits adjust the shunt ADC resolution 9, 10, 11, or 12 bits. Or set the number of samples used when averaging results for the shunt voltage register. Interesting. So, what is the resolution if... Based on the fact that it says mode and samples, and these double, every time. I have a feeling, maybe I'm wrong, I have a feeling that if you define samples, essentially, it runs the analog to digital converter at full resolution and then is averaging the samples together for you, so you don't have to do it in software. So like if you really want like a low resolution, very rough but very immediate, 84 microseconds, you can do a 9-bit sampling of either the shunt register or the current shunt or the bus voltage. But if you're willing to wait longer, it can run either in more precision and eventually even basically it went from 532 to 1.06, 532 microseconds to 1.06. So what it's probably doing is taking two 12-bit values and then averaging them to give you two. So and this is still very quick. So realistically, what we're probably going to want to do is, considering I already said that we're going to be sending this piece of data only 50 times a second, or once every 20 milliseconds, we probably could just run it in this 32 sample mode, because that takes 17 milliseconds to do the conversion, which means we'd have enough time per frame to wow, sorry, brain fart. We'd have enough time to do the full conversion per loop. So I'm thinking we do this 32 sample averaging. Basically, the chip will monitor 17 seconds of power and compute the average amount of power that moved through it during that window, just to lower the overall load. I mean, this is a little pokey 8-bit microcontroller after all. Okay, and so the operating mode. The operating mode settings are selects continuous, triggered or power down mode of operation. These bits default to continuous, shunt, and bus measurement mode. These mode settings are in table 6. And actually, we may want to run less samples. Even though this says 17 milliseconds for conversion, it might actually, if I remember the block diagram, it might actually only have one analog to digital converter that runs through multiplexer. Yep, that's right. Okay, so current and voltage register. Yeah, okay, sorry. So there's only one analog to digital converter, and it runs dual mode. Basically, there's a multiplexer that flips between measuring the voltage and measuring the current. Measuring the shunt and measuring the bus voltage. So we actually want to make sure that we can do two samples within, or two analog digital measurement, two converter measurements per our sampling frame. So we actually probably want to run in that 7 or 8, the 7 millisecond mode, right? Or 8 millisecond, 8.5, because it'll be able to do, so 16 samples averaged. Okay. Operating mode selects continuous, I already read that. But essentially, it's does it read when we ask it, or does it continuously sample and then we just check whatever the latest value is, which is probably what we'll want to do. Continuous shunt and bus measurement. It'll automatically always just sample these values for us, and we just come in and read them, and basically the whole system runs autonomously, or without the chassis controller having to read or trigger these measurements. So data output registers, shunt voltage register address 1. For example, for a value of V shunt of negative 320 millivolts, take the absolute value, including accuracy of 0.01 millivolts, 320. Translate this to a whole decimal number, 32,000. Why does it do that? Convert it to binary. Oh, that's fine. Convert it to binary. It's some value. Complement the binary result. Add one to the complement to create the two's complement formatted result. Okay, so we're just negating it. Extend the sign to create the 16-bit word. Equals 8300 hex. Remember to extend the sign to all sign bits as necessary based on the PGA setting. Okay, interesting. Sign. format. Okay. Okay, they're just... Sorry. A very long-winded... Sorry. Very long-winded way to say that it is fixed point math. It's basically everything's divided by 100, so you get the output's in millivolts, but it's divided by 100. So 32,000 is 320 millivolts. And because it's a 16-bit register, and that means, you could technically have values from negative 32,768 to positive 32,767. So it's literally just a two's complement signed fixed point measurement. Okay, so that's easy. That's just a long way. That's just a long method of saying that, I think. And then all of this is just bus voltage, calibration register, which we'll get into. Okay. On requirements, typical application, register results for amp circuit, probably the math. This is the layout. Okay, yeah. So that means, okay, so relatively simple way to interface to this. Let's go scroll to the guide on what we need to set these registers to. Okay, so how far up do we need to go? Okay, basic ADC function. Okay, here we go. Lots of data sheet that should be read. Let's see. Already read that. Is in normal mode. Okay, so basic. So we got our functional block diagram. We've got an analog to digital converter, which can be switched between the shunt voltage and the bus voltage. And then that feeds into the bus voltage register if we're measuring just the voltage across the rails, or measuring the shunt voltage, which is measuring the voltage drop across the resistor. And then from that, it computes the current and the power draw for us. There's built-in multipliers that does it for us. And then, all right, so basic ADC functions in plus and minus, I already kind of just said that. When the, the INA219 is typically powered by a separate supply from 3 to 5.5 volts. The bus being sensed can vary from 0 to 26 volts. There are no special considerations for power supply sequencing. For example, a bus voltage can be present with the supply voltage off and vice versa. The INA219 senses the small drop across the shunt for shunt voltage, and senses the voltage with respect to ground from the in minus pin for the bus voltage. Figure 13 shows this operation, which we looked at before. When the INA219 is in the normal operating mode, that is, mode bits of the configuration register are set to 111, it continuously converts the shunt voltage up to the number set in the shunt voltage averaging function. The device then converts the bus voltage, same thing. The mode control in the configuration register also permits selecting modes to convert only voltage or current, either continuously or in response to an event, triggered mode. All current and power calculations are performed in the background and do not contribute to conversion time. The conversion times are shown in electrical characteristics, can be used to determine the actual conversion time. Power down mode reduces the quiescent current and turns off the inputs, avoiding any supply drain. Full recovery from power down requires 40 microseconds. ADC off mode, set by the configuration register, mode stops all conversions. Writing any of the triggered convert modes into the configuration register, even if it's the desired mode already programmed into the register, triggers a single shot. Triggers a single shot conversion. So if we didn't do the continuous mode, that's how this would work. You just rewrite the configuration register, and that will trigger conversion. But I believe that all we're going to want to do is all we'll want to really do here is the continuous mode. Although the 219 can be read at any time, and the data from the last conversion remains available. The conversion ready bit is provided to help coordinate one-shot or triggered conversions, blah, blah, blah. Okay. If larger full-scale shunt voltages are desired, the INA provides ranges up to 248 times. Additionally, the bus voltage measurement has two scales, 16 or 32 volts. I believe 16 volts is probably going to be fine here because I'm only running a 3-cell LiPo, which is 12.4 volts, fully charged. 12.6 volts, sorry. Yeah, 4.2 times 3. So 12.6 volts. So we can run at 16 volt mode. INA219 is designed for compatibility with hot swap controllers such as the TPS2490. Uses a high side shunt with a limit at 50 millivolts. The full-scale control of 40 millivolts enable the use of the same shunt resistor for current sensing below this limit. Oh, all right. When sensing is required at the PGA, can be set to divided by 2 to provide a full 80 millivolt scale range. All right. So filtering, I already did this is electrical design, input filtering. I put input filters on this. Okay, so an important aspect of the 219 device is that it measure current or power if it is programmed based on differential voltage. In order for the device to report both current and power values, the user must program the resolution of the current register and the value of the shunt resistor present in the application to develop the differential voltage applied between the input pins. Both the current LSB and shunt resistor value are used in the calculation of the calibration register value that the device uses to calculate the corresponding current and power values after programming. Okay, so let me just stop reading necessarily out loud. All right, so the current least significant bits are set to so 0.0496 is an internal fixed value used to ensure scaling is maintained properly. Okay, so we said that we'll just use Python to do some math. All right, so calibration is you truncate the result of 0.04096 divided by the quantity currently significant bits times the resistance of the shunt resistor. And so current LSB will be calculated as maximum expected current divided by 2 to the 15th power. Okay, so maximum expected current on this. So we're going to switch to a Raspberry Pi 5 at some point. So I'm going to say the regulator in here has a continuous supply rating of 7 amps. It can spike up to 13 amps without failing, but it can't supply 7 amps continuously. The Raspberry Pi 5 that we might use, that we'll eventually use, can draw 15 watts. The camera can draw 15 watts. The GPS probably draws like a few watts. And there's really no other logic devices, so we're going to say that 7 amps realistically is the maximum power that we want to be able to measure. So what we'll do is, so we'll say 7 amps. So current LSB is equal to maximum expected currents, we'll say 7 amps, divided by 2 to the 15th, which is 32,768. And so just to show, so that's our result there. Our calibration value is going to be 0.04096 divided by the quantity, current LSB, times the value of the shunt resistor, which, as I said before, is 8 milliohms. So that will be 0.008. The cal value is 23,967. And we truncate that, so it's just going to be... So truncate is more or less equivalent to round. I don't think round is actually a function in here. Is round built-in function? Oh, okay. Cal equals round cal. Or truncate. That's floor. Okay, that's not... Damn it. All right. Well, we know it's 23,967. So Whatever. Current register. So after programming the calibration register, the value expected in the current register can be calculated by multiplying the shunt voltage register contents by the calibration register, and then dividing by 4096 to obtain a value in amperes. The current register value is multiplied by the program current LSB. Which is a very tiny value. So the value expected in the power register can be calculated by current register times, multiplying the current register value by the bus voltage register and dividing by 5,000. Power register content is, perfect. So, what we shall do, this is hopefully a fairly simple device to start supporting, now that we've gone through the literature. So, but we do need to figure out the gain stuff. So, what does that do? Calibration register and scaling. Okay, power register, calibration register and scaling. The calibration register enables the user to scale the current register and power register to the most useful value for a given application. For example, set the calibration register such that the largest possible number is generated in the current register. So let's see what happens here. So, current register is, so if we had shunt voltage of, power LSB. Shunt voltage is calculated by multiplying the shunt voltage register contents with the shunt voltage least significant bits of 10 microvolts. Okay, so let's say we had a 12. So if it's, let's say 12.6 divided by 10 microvolts. That would be 001. That's 1 millivolt. So 10 microvolts would be 010. Would be, yeah. So that's a lot of microvolts. Let's multiply that by, let's multiply that by the calibration register, which we called cal. And then we'll divide that by 4096. And that will definitely not fit in the register. Hold on. That got to a very big number very fast. Maybe, actually, after programming the calibration register, the value expected in the current register. Oh dear. Shunt voltage is calculated by multiple shunt voltage register content. 10 millivolts. Sorry. Bus voltages are not right aligned. In order to compute the value of the bus voltage register contents must be shifted to the right by 3 bits. This shift puts BD0 in the LSB position so that the contents can be multiplied by the bus voltage LSB of 4 millivolts. Okay, so my division here is just not right. Alright, so 12 point... How do I know what gain I want? That's the real question. Maybe measured shunt INA current. INA can be used without any programming if it's only necessary to read the shunt voltage drop and bus voltage with the default 12-bit resolution, 320 millivolt shunt full scale, divided by 8, 32 volt bus rate. Without programming, current is measured by reading the shunt voltage. Okay, so how do I pick which gain I want? Does it have a guide? Huh. Okay, well, actually, we should be able to figure that out by trying to compute what we would observe in the current register based on shunt voltage. Okay, so realistically, to obtain a value in ampere, the current register value is multiplied by the programmed current LSB, which is a really tiny number. All right. So, all right. Okay. So, the way that we can do this is we would set the way that we can figure out what kind of gain we want. Will be we set the current register to the maximum value we want to possibly measure, and then we check whether we check essentially what that voltage would be to generate would be to generate that value. I don't know, bro. Yes, Brody. Okay. Thank you. All right. So current register is going to be 7 times, or it's actually going to be 7 divided by current LSB. So yeah, so we want, okay, yeah, so because we did that computation of current LSB already, so 3276, reverse the math up here. No, sorry. So if we have a drop of, so 32,768, which is the maximum thing we can measure. So 32, 7 divided by current LSB, so we solve, we move all this shit to the other side. So 7 divided by, so just do some algebra, times 4096. We would divide by the current calibration register, which would give us 5600 in the shunt voltage register. And because that represents a 10 microvolt increment, we can then divide that by multiply by 0. Just shifting the decimal place over by a lot. So that'd be 56 millivolts, which is actually going to be which remember I think our minimum gain is, has a range. Yeah, so our gain of 1 will only report 40 millivolts. So we need to run the gain at divided by 2 for 80 millivolts. I believe. I think that makes sense. Results, shunt average. Well, anyway, so we can always find this out because does the gain amplifier only apply to the current measurement range up to also realistically, 7 Okay, in order, so with this 40 millivolt, we're pretty close. So we could probably, if we're here, hold on, home, times, so 0.001. So how many amps can we measure with the 40 millivolt range? So if we did 0.4. Okay, so 5 amps. So with the resistor that I chose, we can measure 5 amps across the, so 25 watts essentially. So I mean, realistically, we do. That's getting kind of close to what I think it might actually be able to draw. So we'll start here, and then we'll tweak the gain amplifier and see if that actually does anything. So okay, so we'll start by using the 40 millivolt gain. All right, sorry. I've been talking around in circles with no code for too long. All right, let's start this. All right. So we'll go to the registers. And what we're going to do first is we're going to not write these in little, okay. Got this stuff here. So we're going to say, receive packet, send packet, get struct from wire. All right. We'll just, do a good old little copy of this function here. We don't actually need the template. Sorry. Bool. Current sensor or reset. We'll just say what have we receive packet reset. Okay. Reset current sensor. All right. Address. We don't need this buffer. Or do we need this buffer thing? So we got auto red equals I2C master transmit I2C D1. The address is address. The transmit buffer. Okay, so we're going to need a transmit buffer and then null stiff. Is there just a transmit only? Master transmit. No, there's not. I believe these we can just define the receive buffer as nulls and nothing happens. Bytes, number of bytes if set to 0, you want transmit only. Okay, perfect. So our buffer is going to be just a set to the configuration register. So we're really just writing hex 80. Oh, actually, sorry, we got to set the configuration register address first. So configure INA219 configuration register, and then we're doing a hex 80 and then a hex 00. To the idea here is just to reset the bus. So we're going to do a master timeout, and then we're going to give it the buffer, and then size of buffer, and then a null pointer, and then 0. All right. Master timeout if message not equals okay, or oh, that was just a checksum check. If it's not okay, return false. Otherwise, okay, well, return ret equals message okay. All right, cool. Hopefully that'll reset the current sensor. And then we can say, do we set the configuration calibration before power default to 0, yielding 0, current value until the, okay, so no, we set the configuration first. Okay, so we can then say reset current sensor. So we'll just bring that down here at the very beginning of our main thread. After we bring up the I2C units, what we'll do is configure current sensor. And we will just say current sensor, or oops, reset current sensor, and then use the current sensor address. All right, reset current sensor. Perfect. And then we can say configure current sensor. And we're really not going to give it any config. We'll say uint16 config. Well, I mean, that's just really realistically just writing bytes, so we won't do that just yet. So we're going to come down here. We've reset the sensor. We might as well just wait like a millisecond or something, just wait for it to come back up. I believe I have some code in here that does where do I actually, oh, come on. Unpack it. Literally is a piece of code here that calls sleep. I'm trying to remember how I sleep. Oh, perfect. It was literally right below me. ch thread sleep microseconds. It told us that there's like a 50 microsecond or 40 microsecond delay, right? Well, just respect that. I don't know how long it takes to reset. Does it actually? Maybe it tells me how long it takes to reset. System reset, same as power on reset. How long does power on reset take? Reset threshold, power on reset. Doesn't tell me how long that takes. So what we're going to do is we're going to wait a millisecond, because that sounds like a healthy amount of time to wait. So we're going to, we'll wait a millisecond. Sleep for a millisecond, and then what we're going to do is configure current sensor configuration. No, that's lame. Current, all right, I mean, realistically, we ought to just, we configure current sensor address, and then we'll just do the configuration register first, which, come back down here, look at our register, so bus voltage. That's all read only. Okay, sorry. So an example. Oh, that's the shut voltage. Sorry. All right. Voltage range at PG divided by 1. Oh. It has more bits. Maybe. Oh, maybe there really isn't that much of a loss here. Okay. Variable gain amplifier divided by 2. Full scale range 80 millivolts. V shunt. Oh. Okay. That's fine. Configuration register. Okay, so this time we want to do be a bus ADC bits 1 through 4. So that's, or well, the PG bits first. So we're actually going to program reset. That's going to be 0. Bus RNG. The bus range is going to be 0 because we don't need that. So it's going to be 0x. So rather than 3, we're going to have 2. No, wait, sorry. We're going to have 1. Because 0, this is always 0. So 0, 0. We want the 16 volt range. So that's going to be 0. then PG1 for the 80 mil. Oh, that's also 0. All right, so the first bit, so the first nibble's 0, and then for the next nibble, we've got PG0 is going to be 1, so that's going to be 8. So that's going to be, yeah, it's going to be 1. That's ORD 2. What's the, we want to run in, as I said before, we want to run in 16 sample averaging mode. So that's going to be ADC4 is 1, ADC3 is 1. So ADC4 is 1, ADC3 is 1. So it's going to be 1, 1, 1. Then ADC2 is going to be 0. And ADC1 is going to be 0. So, all right, so our next little nibble here is 1, 1, 1, 0. So that's E, right? Got that right? 1, 1, 1, 0. Yeah, so that's E. And then for bus ADC1, we're going to have, I said this was 0. And I believe for SADC, it's going to same concept. Using the same conversion time thing. Averaging conversion time settings are shown as, okay, so it's also going to be 1, 1, 0, 0. So we're going to have 0, 1, 1, 0. That's going to be 6. 4 plus 8, 4 plus 2. That's going to be 6. Yeah, E6. You know what? I've been trying to compute all these. Okay, well, either way, E6. And then the last one's going to be, you know, let's see, 1. Zero. Wait, no, I didn't do that right. Yeah, okay, hold on. We're gonna try this from, remember, we can actually do binary literals in here, right? So 0, 0, 0, 1, 0, 0, 0, 1. No, sorry, it was all zeros. 0, 0, 0, 0. And then 1, 1, 1, 0. Yeah, that's right. I should just be using the pilot. You're correct there, Raphael. Yeah, 1, 1, 1, 0. And so, yeah. 0. We're going to have 0. And then this is 1, 1, 1, 1, 0, 0, 0, and then mode bits, we wanted, want to do shunt and bus continuous. So those are all 1s. So 1, 1, 1. So we can actually just do all of that together. So you can actually use binary literals in C. But yes, that would end up being, 0, E, 6, 7. And then, all right, so we got our configuration register done. And then we want the calibration register, which we did compute as a 23967. Now we actually have to write this little function, right? So we're going to bring that up here. Say bool, configure current sensor. That's going to be uint8 address. It's going to be uint16 configuration, and then uint16 calibration. Do that. We're going to do our buffer. That's going to be the INA219 configuration register. We're going to write the Configuration shifted by, I'm going to do the upper byte because it's MSB first. Shifted 8 and it is 0xFF. And then configuration and to 0xFF. Delete that little bit there. And it didn't sound like we could... I don't know if it'll do the auto increment on the address, because it sounded like it might not, based on the register frame pointer, high speed. It did not sound like it would auto inc the address, based on what we read before. It might let you write, but we're just not going to worry about it. So we're actually just going to... Yeah, sorry. We'll just do it this way. Yep. Acquire bus, do the thing, null pointer, configure current sensor. Well, and then we'll just say calibrate current sensor. Yeah, well, we don't need two functions. Come on. If the return is not okay, then we'll just return false. Now we just need to do this again. Buffer2. Because I don't know if aliasing is fine in C++. It's not. It's not. Buffer2. That's going to be calibration. Calibration. Calibration, we'll just do that. All right. Let's give these better names, right? This is configure buffer. And this is calibrate buffer. And we'll just do the return message is okay thing. And we can just put these up here together. Wire bus, release bus. False, we don't need to worry about the acquire bus again. Ret, and then we can just do ret again, right? All right. So if acquire bus, transmit, if it's not okay, release the bus, return false. And then if we transmit the calibration buffer, we release the bus and check if it's okay. Perfect. All right. Configure current sensor. All right. Let's see if that builds. Make. It's complaining about casting, which is perfectly reasonable. Static cast event 8. Narrowing convert. I mean, yes, it is a narrowing conversion, but we knew that. Okay. Static cast. C++ is a lot more pedantic than C, which is probably a good thing. Static cast. Oh, right, sorry. Okay. Perfect. Okay. So now we just need a function to read all of this data. So we'll write uint 16 get current sensor current underscore t address. And this is literally just going to be I2C master. Acquire bus. We're going to say I2C. Oh, sorry. uint 8. Actually, I forgot one thing. These can be constant. Const uint 8 buffer, or sorry, buffer equals INA219. I'll actually just start by checking the bus voltage register. Should just say, well, I should just call this register. Oh, not ideal. Register buffer. Do that. And then we'll say const uint 8, or actually int 8. Register value. That's going to be 2, and that's not a const. That's equal to 0, 0. Then we're going to do, we'll acquire the bus, and then we shall. And actually, you know what? Just to make the get current sensor register. Won't actually need to do that. Const. Save value. We're going to say transmit. We shall do cd1. Address is address. Transmit buffer is just a register address. The length is 1. Receive buffer is value, and then the size of value. Perfect. And then what we're going to do is if ret is, or well, I mean, if ret not equals message okay, return 0. Say return. 16 or ski. Word equals value. Actually, these are also actually signed, right? So, need to make. I mean, these are uints, but actually need it. Word equals 0. Oh, geez. Let's see. Word is. Oh. Value is int16_t. Actually, sorry. int16_t. Value 0. Zero shifted by 8, ord 2, edit cast int 16, 1, return, actually, we don't even have to do the word thing now, just return _t. Okay, perfect. We have our function to get that. All right, so now that we have that, we can say in our controller update, as part of our update, we'll get int16_t, bus voltage, actually battery voltage equals get current sensor register, current sensor address, and the register address is set by default. So, and then we need a way to send this to the computer. So we'll go in our motion controller types header, and then in our status packet, we will send let's say this is the current sensor int16 battery voltage, and then we're going to set status.battery voltage equals battery voltage. We'll change that later. All right, we can make, right? Hey, we can. So we'll copy this over to the robot. And then what we're going to need to do is, like, looks small now, you know. All right. Where's my Python? There's my Python. What we're going to do here is, hope I'm still connected, right? Yeah, I'm still connected. All right, awesome. We're going to say S. We're going to say AVR dude. Dev motion controller. Flash that, and oh, where did I put this? Motion controller Kybernetes.local. Yeah. Neat. Okay. Perfect. So in our Python code here, we're going to need to go into our motion controller, and we need to add that field to our status packet. IMU status, we ended it up here, so we're going to say battery voltage C int 16. And then in our debug log, we're going to say battery voltage self dot battery voltage. Oh, sorry. Battery voltage. Okay. So maybe this works. We shall see. We'll run our. Let me get up here and put a cone in front of the robot. So we'll run find cone, and that should start printing out all sorts of junk. Oh yeah. Wait for task exceptions never retrieve broken pipe. Oh, you know what? I forgot to update the size of the status packet. Okay, 1315 now because we added 2 bytes. Okay, so make clean make okay. So we're gonna flash the motion controller. And then run our find cone. See what happens. Well, it's doing stuff, so we'll pull that. No, it's not moving. Interesting. Oh, all of this is very not happy looking. Battery voltage is 0. That's not good. Why is it not moving? Other than something clearly is going wrong. Did I attach power? Motor controller's running. Alright, well, you know what? We're gonna... Well, we revert. Okay, right? Oh, did I define the sizes up here? Maybe? No, I don't think so. Oh yeah, well, we'll comment that out. And remove that. And then we'll remove the whole battery voltage thing. Bring this back to 13, right? Not do that, not do that. Make sure that this whole thing still works, right? Okay, SCP, raise.local. This little current sensor thing that crashed us, right? All right. Find cone. Interesting. I messed something up. I must have messed something up. Oh, well, now it's really running, okay? Alright. Well, shoot. Alright, / remote control. Well, let's see if we can get the, realistically, let's at least just get the if not setting the battery voltage thing, at least let's just set the value to something just so we can figure that the packet's going across correctly. So we'll do that up to 15. Add our int16 battery voltage. Come over here, we'll undo those changes we made. int16. Battery voltage, perfect. Okay. So from there, we'll just make SCP. Did turn off our that. Okay, AVR dude. Thank you. Find cone. Hopefully that'll come up as a value of 42. Yeah, battery voltage equals 42. So the whole sending the additional value in the packet's fine. So now we just need to figure out why the sensor locked things up. Okay. So let's see if that actually did what I thought it just did. Let me see if that actually caused us woes. Maybe we didn't release the bus correctly. No, we released the bus correctly. Acquire bus, release bus, register address, 1 value, size of value. Well, anywho, okay, we copied that over. We'll flash it to the robot. Yeah, reading that sensor is causing it not to function. It was very disturbing. Yeah, that's very unfortunate. Why would that be happening? Unless I'm using the wrong address or something. Because we're not using the master transmit timeout. So what we'll do, sys interval. We'll say the timeout is 100 is 5 milliseconds. Right? Alright. 5. Sys interval. Number of ticks before operation timeouts. So we're going to say, I think there's like a CH, like a CH ticks. Like a ticks per millisecond or something? Nah. Oh, CH time MS2I. Okay. Okay. That doesn't seem right. Where is it pulling this information from? Who knows? Some tick. That looks like it's an RT and not... Oh, interesting. It's just not a function that's in the nil kernel. It's in the... Either way, I make... So at least now things will time out if it's not working correctly. It'll still, maybe it won't break our robot. Oh, there's probably an INA. I mean, there is definitely for Arduino, like through the Arduino SDK. I just don't know if anybody's written one for ChibiOS. I mean, I could Google that and see if somebody did, but the idea was I'm trying to see if I can do it myself. I've done something wrong. Okay, well, let's see. If using a timeout, let's see if using a timeout helps me. No, still dead. Interesting. That's weird. Okay. What did I do? What did I do? Actually, 7 bits without the RW bit. Oh, well, that might mean that I need to shift this by 1 bit, possibly. But, I mean, that shouldn't kill the... Oh, it might be broadcast because... Oh, okay, I just don't know what ChibiOS does on that one. Okay, let's see if that works. ChibiOS 7 bits without the address. Okay. We are dude. 364 bytes. Oh, hey, now it's working. And the battery voltage was updating. Okay, cool. So the problem was, okay, so the problem is that typically in a lot of ways, or in a lot of data sheets, the I2C addresses are written as 8-bit quantities, even though they technically only have 7 bits. Sorry, so yeah, the I2C address, it's an 8-bit field, but the last bit means read-write. So some data sheets will write the whole 8-bit address just with the last bit always cleared. And then some will write it as the 7-bit address, essentially assuming that last bit isn't there. And ChibiOS expects it in that 7-bit with no bit on the end format. So if your datasheet says the address is hex 80, you actually need to right shift it by 1. So that's what the problem was. All right, cool. So yeah, so battery voltage 21762, and we programmed the gain amplifier, but we divided it by, hold on. Trying to make sense of this value, because I know if I plug it, I think I tested the voltage on this battery and it's like 11.3 volts or something. So let me just double check on that one. So if I plug, me just not explode my everything here. Alright. So, the voltage, if I measure it, I can actually get good contact on my probes. Okay, voltage, DC voltage is at 10.93 volts on the logic supply. So how does that correlate? 21762. Oh, if we did the math like I'm supposed to. So yeah, I said 10.3. So 21762 divided by 2. Oh, sorry, I'm not in Python. 21762 divided by 2 is, well, that's saying 10.8 volt. And I did the divide by 2 because remember we set the gain amplifier at a division by 2. So that's 10.8 volts according to it, which doesn't make any sense. But maybe I did something different. Bus full scale range. What if I actually programmed the full scale range? Maybe that's the register. You know, let's just see what happens. We just got to flip one bit in the configuration. So if we did the full range, so if we change that 13th bit to 1, we made this, copy that back over, go back to our, back the robot up here. No, sorry. Oh well. So we'll do AVR dude. And then we'll do our little remote control program to back the robot up. Okay. Kill that. We'll run find cone because that was actually printing log messages, right? Oh god. The syncing is one of the things that took a dip, if anybody remembers the last video. Let's see if the bus voltage thingy changed, although that might not have done it. No, it didn't change at all. Okay. Well, now it's 21,786. instead of 768. 94. It went up. That doesn't make any sense either. So let's just leave this at the way it was with 0. We did the gain by 2. Note the default's divided by 8. Table 4 shows the gain in range. Samples used. Actually, hold on. Was that right? It was 21,786. 21,786 divided by 2. It's 10.89. Hold on. Let me just double freaking check this again. I might have just had a bad contact because I thought this battery was at a higher voltage. But that was an open circuit voltage. Oh, I can't read. So yeah, it says if I squeeze the probes in here real nice and good. Oh yeah, 10.92 volts. Okay, actually it's reading perfectly correctly. That's good. That's real good. Okay, nice. And there's gonna be a tiny little loss over the shunt. So 10 point, the fact that it's like 10.93 to 10.89. That's 0.04. It's 40 millivolts. Like, yeah, like, whatever. Like, I don't care this 40 millivolts off. Okay, perfect. So it's that whole gain amplifier thing that we changed. because we did the gain of the divide by 2, it's going to multiply all of our... I guess that means it multiplies all of our measurements by 2, because it's trying to measure a smaller range. What if I set the gain amplifier to 0? Or to 1. So we did 0, 0. So 1, 2, 3. What if we did... Yeah, what if we did 0, 0? So, you know, a gain of... 1. What if we did that? You know, so 1, 2, 3. And so if we did 1, 2, 3, 1, 2, 3. Yeah, because it's programmed to 0, 1 right now. What if we just did 0, 0? Oops, 0, 0. Wrote the motion controller and did a find cone program. The battery voltage is the same. I don't know what's going on here. Maybe the gain amplifier is not. It probably mentioned something. It probably mentions something at PGA shunt voltage register bus voltage. Oh, well, I'm stupid. Well, no, I'm not, but I'm okay. Oh, okay. I'm so sorry. Okay. Bus voltage register. The bus voltage register stores the most recent bus voltage. The LSB it's in units of 4 millivolts. It's in units of 4 millivolts, and there are some flags on the end of it. So okay. 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 Conversion, although the data from the last conversion can be read at any time, the conversion ready bit indicates when the data from the conversion is available in the data output registers. Okay, so we actually have to do is not what I did, so we gotta... Oh dear. There we go. Alright. Leave the gain at what it was supposed to be. But what we actually have to do is... So we got bus voltage. Okay, we got bus voltage register. We actually need to do bus voltage register shifted 3. So divide by 8 and then multiply by 4, which would be divide by 2. Okay, that's how we were getting that. Okay, I get it. Bus voltage register. Okay, so shifted right by 3, which is division by 8, and then we would have to multiply it by 4 millivolts per division for a full voltage of. Okay, that's how it works. That's why it was divided by 2. Okay, that makes sense. Battery voltage is division by 3. Shifted back by 2. Okay. Well, times... Well, actually, it's in units of 4 millivolts, so... Yeah, multiplying by 4 would give it to you in units of 1 millivolt, which is why it was in... Okay, I like it. Go. We'll have to break out all these little definitions at some point just to make this not horrid to look at, right? Bit 13 is 0, bit 13 is 0. Okay, good. So now what we really need is looking at the current and the power and all this other stuff, right? So let's pull out the other data. Motion controller types. Battery voltage, int 16. Current. Battery, actually, realistic battery power. Okay, nice. We'll do that. So then we need to add another 4 to this. So that'll be 19. Come over to our Python. And battery voltage, battery current, battery power. Okay. I gotta read all this data out of the thing. Battery voltage. Okay. Sensor address register power equals get current sensor register, current sensor address. Okay. And if we remember how it wrote these out. Operating mode. Anywho, okay. A PGA divided by 2. Shunt voltage register LSB is 10 microvolts. I mean, that's fine, but actually read the current register or the power register. Well, anyway, we can just figure out the math. We'll math it later here. Okay. So make, copy that to the robot. We will flash the motion controller code. And then run find cone. Okay, we got a couple of samples. Okay, battery current and battery power. 2400, 4418. All right. So if we remember, what kind of math are we doing here before? So with our, oh, that's in Python. Python, with our gain that we had, I'm going to recalculate all this. LSB, cal is equal to that. We did our whole 7 divided by be 56 millivolts, but we're dividing by 2, so should 28 millivolts will be 7 be 1 0.4, right? 1 amp. Actually, that's a good question. Battery current is actually in current. The current register is capable of multiplying the shunt voltage register with the value in the calibration register. So shunt voltage of 0.4 volts times cal is 95. That's not right. What if we did 7? Right? 71. That's not right. I did something wrong. Oh, we need to divide by the cal register. Okay, multiplied by the cal register. So we would need to. Oh, I fucked up. Hold on. So 1 amp would be 4 millivolt drop. Well, after the gain amplifier. Anyway, sorry. Yeah, you need a full scale. Yeah. Trying to make sense of what I am seeing. Yeah, battery voltage. Yep, there we go. 10.86. That was, or 10,864 millivolts. Then yeah, so multiplying the shunt voltage with the value in the calibration register, right? So if the shunt voltage was 4 millivolts and you multiply it by cal, it would be we already did that. Okay. Right. Running the calibration register, current register, shunt times calibration. By 4096. Oh. Multimeter was mad. Okay. Register contents. Well, maybe we just multiply it by 4096 divided by. If we were to say 4418 divided by, it's realistically 1 something, divide by volts times cal, so we would multiply by times 4096. So, then we got to divide by 2, right? Wait, to obtain a value in ampere, the current register value is multiplied by the program current LSB. Providing the calibration register value expected in the current register can be calculated by multiplying the shunt register contents by the calibration register and then divided. To obtain a value in amperes, the current register is multiplied by the program current LSB. So 4418 times current LSB. Oh, right. Okay. Which is 7 divided by that range, right? Okay. So because we're trying to scale, right? As you said, Raphael, I don't know if this is actually what you're referring to, but the whole point of this entire thing was to map 7 amps to the full range of the amplifier. So if we've programmed that, then we want the least significant bits here to be, I mean, let me just multiply this by that range thing that we did. So it would be this divided by what it could be, you know, converted a range 0 to 1 and multiply it by the range that we programmed. All right, presumably. Now, what would be interesting is it looks like when you change this gain amplifier, it actually fixes all of the data for you, maybe. Because, like, yeah, divided by 8, it's, you know, SD14... SD30, it's always SD like 12 here, so it might actually just fix the range. I don't know. Anywho, so yeah, so presumably we're drawing 943 milliamps, which makes sense because the camera's on, which, you know, could pull up to 5 watts technically. The Raspberry Pi is on, which it's a Pi 4, so it can probably pull, you know, upwards of 10 plus amps, or 10 plus watts. Which it, I mean, there's not much load on the Raspberry Pi, to be fair, so I don't know how much power it's pulling. But, you know, I really wish I actually had something to compare this against, because I mean, theoretically, I could try to splice my multimeter here into my power system, which would be, you know, actually a way to measure it. But I just don't have a good way of setting it up right now. I don't have any alligator clamps. But I mean, that does make sense. Yeah, 943 milliamps, and that would also mean that. How about power? Power register. The value expected multiplied by, okay. Power register is multiplied by power LSB, which is 20 times current LSB. So we'll say power LSB equals current LSB times 20, because that's what it said to do. The value expected in the power register, blah, blah, blah. Power register content is multiplied by power LSB, which is 20 times the current LSB for a power value in watts. Current value by the bus voltage. The value expected in power register can be calculated by multiplying the current register by the bus voltage register and then divided by 5,000. The power register content is multiplied by power LSB, which is, okay. Well, 943 milliamps. So, well, let's see. So it was 2400 times power LSB, which 943 milliamps at, you know, 10.8 volts would be pretty close to 12, pretty close to 10 watts, which, okay, we see, because you have 10.864, you know, times 0.943, right? Yeah, there we go. Same thing. So multiply this by the power LSB, and yeah, we get power in watts. Pretty damn close to it anyway. So yeah, I don't want to do any floating point math on the. I don't want to do any more floating point math on here, right? But I mean, We could do it in fixed point. No, that would be a horrible idea. Okay. So just to make it easier to look at, we're gonna do a horrible thing and just hard code some of this shit. Format. Battery voltage divided by 100.0. Current. We're gonna make this programmable, at some point. But this is just hacking. Don't do this. Or hacking things together. Don't do this. Battery current divided by 6937.0. No, what the fuck? Sorry, no. Power LSB, current LSB is calculated as 7 divided by I don't think that works. Does it? Maybe? Alright, really need to be constants, but we're just hacking things up just to make things easier. See if I broke Python here. Oh, there we go. Need to divide by 1,000. Oops. But yeah, battery current, battery power. There we go. Very, very nice. Oh, A-Y-I. Mess that up. Yeah, I. Divide by, this is not voltage, volts, amps, and watts. Okay, we're gonna fix those constants here at some point. Current LSB equals 7.0 divided by 2 to the 15th. Power LSB equals 20. real question here is if I get this remote controller thing to spit out a something, or not something. I mean, if I log the power in here, right? Maybe I would. What do you call it? Wow, brain fart again. If I logged the power coming from the remote control thing, maybe I could see lower power draw due to the fact that the camera's not running. I don't know what the camera's idle power is. So we'll go to this remote control program. And I mean, we're going to say arm, wait until drivable, set while not, set steering. We're just going to say get status. We're going to say print. Curious. Yeah, with the camera not running, we're at 6.97 watts. Yeah, 6.8 watts. That's with the camera down, because this is just the little remote control program. And if we actually run this find cone thing, oh, well, if it didn't crash. So if we do find cone, we can see that we're actually pulling more, like 10.2, 10.4 watts, because the camera's running. Running a little AI model to detect the camera. So, okay. The current sensor and power sensor is in fact working. We can measure the battery voltage, the current draw on the battery, and we can measure the thank you, Raphael. Thank you. All right. So I think, I mean, it's 9 o'clock. All right. Essentials with the camera active in any capacity, would it still capture effect draw post video? Well, it's well, the camera is pretty active when it's doing that find cone thing, the find cone task, because it's running in find cone. It's running a YOLO v7 based object classifier, and it's also running a video encode. So it is capturing the video, encoding it, and it is also capturing the video, or sorry, I should say, it captures the video, encodes the output, and also then downsamples that image and then feeds it into a YOLO v7 model. So the fact that I don't actually know what it, you know what? Actually, we can find out. What is the idle power? So let's drive the thing back over here. I'm going to unplug the camera and see what happened. Sorry, let me just bring it back over here. Okay, so we knew what it was drawing. So we see this 6.7, 6.9 watts. The camera is plugged in but not running. We saw that it was drawing, 10-ish watt, 10.2, 10.4 watts when it was doing its active task. So about a 3.6 extra watts. So if I unplug the camera, make sure I unplug the right cable. All right, camera's now unplugged. If I rerun this remote control task, and well, everything blows up in my face. we can see, now it's at 5.7 watts instead of, there was a lot of crap that it wrote out. Instead of, we were at what, 6.7, I think I said, right? 6.7 watts. So its idle power appears to be around a watt, which is, not great, not terrible. And then its output goes up by another, its consumption goes up by another 3.6 to 4 watts running that object classifier and doing the video encode. Realistically, the fact that you can do a 4K video encode and run an object classifier at 60 FPS on a dedicated device, in the span of 4 to 5 watts, that's pretty cool. I guess a phone SoC also draws like 5 watts at full tilt, so maybe it's not actually so impressive. But yeah, so there we go. So in any so just idling there doing nothing, it pulls a watt, and then running a lot of its hardware at the same time, it pulls another 3.6 to 4 watts. Hopefully that answers your question, Danish. Let me put the camera back in before I forget and wonder why the heck this isn't working. All right, cool. Let's plug it back in. Let's see if fine cone works now again. It should. Perfect. All right, it worked. Cool. Battery voltage, battery current, battery power, 10 watts. All right. Well, and I think the logic battery is a 80 watt hour battery. So hypothetically, in this mode, I can run for 8 hours. It'll never quite get that. Theoretically, I could run for 8 hours. It's probably gonna be more like 7. But yeah. So I think that's a good stopping point for today. I'll get this code pushed. All right, let's just do that right now. So we'll do. It's not like I've. There's magic values in here, but 890 lines. I don't like how long this file's getting. We'll try to. We'll have to. Either I'll do it off stream or we'll do it in the next. I'll do it off stream. Nobody likes watching. Nobody likes watching the boring parts of refactoring. But I might do it off stream. I'll probably do it off stream. Maybe I'll do it on stream. Try to refactor some of this, at least into other files, if not like ChibiOS drivers. I think that would be fun anyway to distill out of this would be actually going into implementing those GPIO interrupts for ChibiOS, because I was actually looking around, and so like in let's say this is the Raspberry Pi Pico backend for ChibiOS. We can see that there's this like PAL low level driver enable line event, enable disable line event, force line event logic. That is how these pad interrupts work, and also in the STM32 driver, we can see, like enable pad event. We see these like logic things that set up interrupts, but if you go to the AVR, enable pad event. Oh no, to do implement. So maybe a fun stream would be at some point would be implementing this support in ChibiOS and pushing a contribution, right? Or seeing if they're interested anyway, right? But at the very least, at least refactor some of this so I don't end up with a gargantuanly long single file here, right? At least, but either way, maybe I'll do that. That's a different stream topic. But next week, what we'll do is we'll start actually working on the IMU. Because I really, the whole point of this ChibiOS migration in the first place was to have better I2C performance on the AVR. So, or to use somebody else's better implementation of I2C on the AVR. So next week we're going to be looking at the IMU that I added, which is called the USFSMAX And yeah, I don't want to. I've mentioned this thing a bunch, not necessarily on stream, but just to other people. The specs look cool. I've no business, relationship, personal, whatever, otherwise with this guy. There's some Tindy page I found. Where is this whole thing? He said, yeah, USFSMAX. He's just either way, this is an IMU. It handles all of the motion fusion stuff on board. It's based on the little ARM microcontroller, so I'm not talking about like mysterious DMP support or something. It has updatable firmware. He doesn't. The sad thing is, the manufacturer does not give you the code for that's running on it, but they're claiming 0.3 degrees of accuracy, and I have not been able to test this at all yet because I haven't got the dang thing working. But next week we're going to start evaluating this and implement ChibiOS support for this USFSMAX. And unlike what we just did, there's a lot of reference code for this thing, so we're going to try to convert their Arduino sketch, their Arduino driver over to run on top of ChibiOS. So that'll be next week's stream. Hopefully we can get it working. I'll admit I played with it a little bit and I had trouble with the calibration of the thing, which what else is new? I have so much trouble getting magnetometer calibration to work. But anyway, so next week we'll do the IMU. But I think this is a good place to leave this for tonight. Thank you all for watching. Thank you all so much for watching. Glad I got this to work. It was nice. Let me just sit here in silence for a little bit to sync up with YouTube because I think my OBS is about 10 seconds ahead. All right. Thank you all and good night.